Hello, and welcome to the SDC EMEA presentation, Computational Storage, How do NVMe and SNIA Computational Storage Work Together? I'm Bill Martin from Samsung. I am the SNIA Technical Council co-chair. I am also the editor for the SNIA Computational Storage Architecture Specification and the SNIA Computational Storage API Specification, and also co-chair of the NVMe Computational Storage Task Group. So today I'd like to talk to you about an overview of the SNIA Computational Storage Model, an overview of the NVMe Computational Programs Model, and then the NVMe to SNIA mapping, and finally a summary of how the two map to each other. So with that, let's get started. I'm not going to go into detail about the SNIA computational storage architecture, but I would like to briefly start out with the fact that within that architecture, we have three different versions of computational storage devices. There is the computational storage processor, which is the simplest of the devices. The computational storage processor is a standalone processor that has access to storage, but does not actually contain device storage on it. Next is the computational storage drive. It is the same as the processor, except that the storage is actually on the computational storage drive. And finally is the computational storage array. And the array has two or more storage devices. They may actually be computational storage drives, or they may simply be storage drives. It has computation, it has an array controller, so that the entire array appears as a single computational storage device, even though it may have multiples. For what we're talking about today, I'm going to focus on the computational storage drive and the model for that. So first, I'd like to talk about what the architectural elements are for the computational storage drive. For the computational storage drive, we have computational storage resources. That's this area shown in the light blue. It contains everything necessary for computational storage. Within that, you have a computational storage engine. This is the engine that actually performs computation. This may be a logical construct or a physical construct, but it is the construct that actually performs the compute. Within the computational storage engine, the model has a computational storage engine environment. That must be activated on the computational storage engine in order for the computational storage engine to do anything. The computational storage engine environment could be a Linux kernel or some other kernel. It could be a Docker packet processor that processes packets. It could be a FPGA or ASIC environment. It is possible that the computational storage engine environment is virtually there and not an actual physical entity, but it is still there from a model point of view. Attached to or activated on the computational storage engine environment is a computational storage function. This is the actual function that you are going to be performing. It is possible that the computational storage function is automatically activated on the environment and that the environment is automatically activated on the engine, but each of these elements is logically there. Next, in the light purple, we have the resource repository. The resource repository is a location where the host can download computational storage engine environments and computational storage functions. There may be downloaded ones. There also may be preloaded computational storage functions and computational storage engine environments within the resource repository. These are things that can then in turn be activated on a given computational storage engine. Next, we have the function data memory. The function data memory is the memory where all data for use by the computational storage engine resides. That data is then allocated to a particular computational storage function execution, and that data, once it's allocated, is allocated function data memory. Finally, in this model, we have the device storage. The device storage is the physical storage where you write or read your data from. It is NAND flash or something else of that nature, depending on what the nature of your computational storage drive is. So next, I'd like to go over a brief model of the NVMe computational storage architectural components. This is a work in progress within NVMe, and it is subject to change, but this is the current state that the architecture is in within NVMe. So within the NVMe model, we have compute namespaces. They're over here on the left, highlighted in a dark gray box with two of them in light yellow. These compute namespaces contain a compute engine, and they contain the programs. And we'll talk in the next slide about how these terms map. Programs are what operate on data. They operate on data in the subsystem local memory. The subsystem local memory in the center of this diagram includes the program input data and output data. And finally, we have the NVM namespaces, which is the persistent storage of data. These could be an NVM namespace, a ZNS namespace, a KV namespace, but they are basically the NVMe architectural component where data is actually stored. So how do these terms correlate? So the SNIA term computational storage engine, that's equivalent to the compute engine or compute namespace in NVMe. The term computational storage engine environment at the moment within the NVMe model is virtual. It is not defined within the NVMe model. But as I said, that is an acceptable application of the SNIA model. Then we have the resource repository. The resource repository has downloaded CSFs and preloaded CSFs. These are equivalent to the programs that were shown in the previous slide. In NVMe, these are called programs as opposed to functions within the SNIA architectural model. But we still have downloaded programs. Then we have device-defined programs, which are the equivalent of the preloaded functions in the SNIA model. One of the big differences between the SNIA model and the NVMe model is that the resource repository in the SNIA model is a global repository that is available for any computational storage engine. In the NVMe model, the programs are downloaded or defined on a per compute namespace basis, or therefore on a compute engine basis. Next, we have function data memory. This is the same as the subsystem local memory that exists in NVMe. The allocated function data memory is equivalent to something called memory range sets in NVMe. And on the next slide, we'll see that a little bit better. And finally, you have device storage in SNIA is the equivalent of the NVM namespaces. So let's look at that graphically. First, we have the computational storage engine that maps to the compute namespace. you will see within this diagram that within the compute namespace, we have programs. These are the equivalent of the CSFs in the SNIA model. And as I mentioned earlier, you have downloaded or device defined, which are the equivalent in the SNIA model of downloaded or preloaded. As I mentioned before, these are on a per compute namespace basis. What they would map to effectively is that they are downloaded into a computational storage engine environment within the SNIA model. So there is a slight difference there. Next, we have the function data memory. As I said, this maps to the subsystem local memory. The AFDM maps to something called memory range sets within the NVMe model. These memory range sets are a construct that are created on a per compute namespace basis, and they identify ranges of the subsystem local memory that are to be used by a specific instance of a program within that compute namespace. And finally, we have the device storage. The device storage maps to the NVM namespaces, as was mentioned earlier. These could be NVM, they could be ZNS, they could be KV. But the mapping from device storage maps directly to the NVM namespaces, which is where data is stored in NVMe. So in summary, SNIA is a general architectural model for computational storage. It is intended to be a model that can be used by multiple protocol layers, not a single protocol layer, so it does not get down to the specifics. It has a flexibility for that variety of protocols. NVMe is a specific I/O command set for computational programs. It is specific for the NVMe protocol. So it uses the NVMe queue structures for sending commands, getting completion entries, etc. And it is very specific to NVMe. It has NVMe log pages, NVMe identify data structures, and so forth that are all protocol specific. At the Persistent Memory and Computational Storage Summit, there were some additional sessions that were included at that summit. The names of them are the latest efforts in the SNIA Computational Storage Technical Work Group. This was put on by the SNIA CS TWIG co-chairs. There's another one that is NVMe Computational Storage and Update on the Standard. This was put on by my other two co-chairs on the NVMe Computational Storage Task Group. And finally, Programming with Computational Storage that goes through the SNIA Computational Storage API. All of these are available on the SNIA Educational Library site and can be viewed. They are very helpful if you want to understand the in-depth details of what's going on with computational storage, both in SNIA and NVMe. So with that, if you are interested in computational storage, I would encourage you to join both SNIA and NVMe in their standardization effort. I would encourage you to go look at these additional videos. I hope that this has helped to give you an overview of the computational storage mapping between SNIA and NVMe. So thank you for your time. Please take a moment to rate this session. Your feedback is important to us. We do look at it. Being on the technical council, it is very important to me personally to know what you think of each and every session within this conference. So again, thank you for your time, and enjoy the remainder of your day.